Deep theorems such as divergence and Stokes' theorem will depend on our deep understanding of surfaces and how integrals happen along them. But what is a surface to begin with? We want to have a mathematical object that describes a sheet of paper or some other elastic object sitting in the 3 dimensions. Even if they enclose a volume, by a surface we only talk about the shell, not the inside volume of the shape. The first instance of a surface we see is described through a function. We have a function of 2 variables, f, and if we graph it in 3 dimensions by putting the values of fx, y on the z-axis, we end up with a surface. Its shadow describes a region D in the xy plane, and for every point in D there is a unique point in the surface on top of it. In other words, its shadow, its projection is exactly the point we fixed. For these surfaces we saw a few things. For example, we saw how to find the equation of the tangent plane. I want to leave them as exercises for you. You can find from previous section. How do you find the equation of a tangent plane at a given point to this surface? What is the equation of this plane? Which means find the normal to the surface at that point. How do we find the area? How do you measure how much surface area it is? How much paper will it need to construct this surface? And later we will learn how to do surface integrals of scalar and vectors along them. So for each description of a surface, you should be able to answer these 3 questions and have formulas for them. The next description of a surface is describing a surface as the level set of a function of 3 variables. Here this is a different f, it's in 3 variables. And under some regularity assumptions on that function, for almost every constant, the level set, the set of all points which map to the same quantity, will form a surface. The sphere, for example, is a prime example, where the function here, f, on this side is equal to the constant, positive constant, will produce the surface of the sphere. These in pieces, if we break them up, if we decompose it into pieces, each piece can be described using the previous method. You can describe one of the variables as the function of the others, but this cannot be done in one go. As you can see from the surface, none of the variables is a function of the other 2, because for every point in xz plane, for instance, you find 2 points, 2 values of y that correspond to it. My coordinates is a bit messed up, but that wouldn't matter anyway. So for this, you have seen the equation of the tangent plane. What is the normal? Actually, this is easier even than previous case. What is the tangent plane's normal in this case? We don't want to learn how to do integrals and surface areas with this description. It's not too easy. Basically, we have to go back to the previous description or the parametric description that is coming up next, surface integral. So these are easy to write down, as you see in the case of a sphere. But if you want to do any calculation with it, we have to solve for z or something, and all of a sudden you end up with much more difficult formulas. Now, the topic of this section will be to look at surfaces from a totally different coordinate system and to parameterize them. This is analogous to how we described curves. Even in R3 or in R2, to describe a curve, for example, this upper half of a circle, we would go to a new parameter t, which lives in one dimension, and then we say there is some AB and there is a function RT which describes this curve. For example, here that will be cosine t sine t. So to describe a curve which is one-dimensional in nature, it's a line but it's bent in the two dimension, we can still go back to one parameter, and one parameter here, just t, is enough to describe it. So by analogy, here we have in reality a two-dimensional object because it's a sheet of paper, but it's bent into the bigger space, and we want to take away that curvature thing, that bending thing. We still want to have two parameters and be able to describe our curved surface by those two parameters alone. And the analogy continues. We just want a function that takes a point in our parameter world, a point here, and maps it to some point here. So that will be r evaluated at uv, and uv is some point here. If this function has some nice properties, then we can recover every property imaginable about the surface from just derivatives and integrals of r. For example, we can find the equation of the tangent plane to the surface. The reason we introduce this is that we can more easily talk about surface and more easily compute the surface area and surface integrals. This one we haven't seen before, even in the case of z equal f of x y case, we haven't seen this happening. So surface integral of scalar and vector functions along the surface.